So yeah, I'm going to tell you about, I think, one of my favorite seminal results in the theory of reinforcement learning. And this is about how to do exploration in Markov decision processes. So maybe let's start out just by talking about what reinforcement learning is. So reinforcement learning is a paradigm for sequential decision making in which an agent interacts with an environment to accomplish some task. So just like to keep an example in your mind, think about this robotic hand that's trying to manipulate the Rubik's Cube. So maybe the state is sort of like the robot manipulates its joints and forces to, in response to this environment that's governed by the laws of physics, to accomplish a task, which might be like get the Rubik's Cube into a solved state. And so, these problems are very natural, or this framework of reinforcement learning is a very natural fit for problems in robotics. These techniques have also been used in many other places, like playing two-player games like Go. And when DeepMind, achieved human-level performance in Go using reinforcement learning techniques, this was seen as an AI breakthrough. On the right, I'm actually showing you a application of reinforcement learning in mobile health, where they're trying to sort of nudge people to stand up and maybe be a little bit more active. And so these techniques also have applications in health and tutoring and many, many other places. So there's like a widespread potential for applications. And because in part these AI breakthroughs and this widespread potential, recently the field of reinforcement learning has been gaining a lot of interest, both from the empirical machine learning AI community and from the theory community as well. And so I just wanted to tell you a little bit about some basic techniques here and maybe give you some pointers for where to go if you want to pursue this direction. Maybe one thing I'll say just as a motivation, a lot of the successful applications of reinforcement learning today, like solving Go or even this robot solving the Rubik's Cube, these are problems where for some reason you actually have tons and tons of data. Meanwhile, the one on the right, this mobile health one, is one where you actually don't have that much data. And so there's actually some opportunity for more statistical thinking in this problem. So when we start to think about how to design efficient algorithms, we run into three challenges. These are exploration, generalization, and credit assignment. So exploration is this question of how to collect data in a way that allows you to learn efficiently. And if we think about this robot manipulating this Rubik's Cube, if we just sort of like perturb the joints of the robot randomly, we'll like almost never solve the Rubik's Cube. So we may not even figure out what task we're trying to solve. So you actually have to be much more deliberate about how you perturb the joints of this robot so that you explore what's going on and figure out what task you're trying to solve. So that's exploration. Generalization is about leveraging experience from other situations to make good decisions or good inferences in new situations. And this is actually what supervised learning is pretty good at already. So right now, if you train a classifier to predict dogs from cats from images, I think you would expect that the classifier does pretty well on images it hasn't seen before. This is like what this training and testing set is doing. And so we want the same kind of ability in reinforcement learning agents, this ability to generalize to new situations. The last challenge is credit assignment. And this one is about how to, when you make a long sequence of decisions, how do you decide you make a long sequence of decisions and you observe some outcome. How do you decide which decisions were good or which decisions were bad or which decisions actually contributed to that outcome? Even as a human, if you are trying to solve a Rubik's Cube for the first time, you're going to do many things that are wrong or useless or whatever. And if you eventually do solve the Rubik's Cube, you want to sort of infer which of those moves you made were incorrect or took you backwards or useless. And doing this is sort of like we want to allocate credit to the past decisions that we made, even though we did the solve. So these are the sort of three central challenges. And one thing that the community has been doing is actually trying to isolate subproblems that focus on addressing one or two of these challenges at a time. So there's a subproblem called contextual bandits, which focuses on addressing exploration and generalization. These are problems where you're still making decisions in an uncertain environment, but somehow your decisions don't have long-term consequences. Like whatever you do today affects only what happens today and not what happens tomorrow. So you don't have to think about when you made a long sequence, which moves you made were useful or not useful. That's contextual bandits. And this problem is actually quite practically useful in its own right. Then turning to generalization and credit assignment, there's a bunch of methods in this. They're called like policy search or policy optimization methods. There's a bunch of different formulations here. Another formulation is called offline reinforcement learning. Another one is called imitation learning. These are also becoming quite useful in their own right. And these are problems where, for whatever reason, you don't actually have to explore. Someone is like exploring for you, perhaps. And so this allows you to focus on how to deal with these long sequences of decisions and very, rich information like that you want to generalize off of. And finally, and the one that we're going to talk about today is actually addressing exploration and credit assignment. And this is what's called tabular reinforcement learning, or it's going to be a setting where you actually do have to make a sequence of decisions, but the states and the actions you're thinking about will not be so rich. And so you won't actually have to generalize. So that's what we're going to talk about today, and we'll dive into some more details. So the basic protocol, or the model for studying these tabular reinforcement learning problems, is called the Markov decision process. And the picture you can have in your mind is like this robot. The robot is walking around in some world and trying to get to the charging station, which is depicted by the lightning bolt. And so what happens is the robot is going to interact with this world and try to get to the charging station. And it does so by this iterative process, where at each step, the agent is going to observe the state of the environment and take some action. The environment is going to update its state, and the agent may receive some reward for being in some state and taking some action. So maybe you can think about the states as the positions of the agent, the robot. The actions may be like north, south, east, or west, which direction the robot wants to move. The environment, if the agent is in the top left corner and says go east, maybe the environment will move the agent one position to the right. And maybe the reward will just be like the agent gets some reward if it makes it to the charging station and doesn't get reward otherwise. And the goal of the agent is going to be to try to maximize the reward collected. So this is sort of like the high level protocol. I'm going to start turning into the math details now. So again, we still have this robot trying to charge its battery. And the ingredients to model this problem, there's a bunch of things. So there's a set of states. I'll denote this calligraphic S, a bunch of actions, calligraphic A. There's a transition operator, which describes a distribution over the next state if you're in some state now and you take some action. So it's a mapping from the states and actions to distributions over the next state. Then there's a reward function, which describes how much reward you might get if you're in some state and you take some action. And this will be like some distribution that I've normalized to be in 0, 1. This doesn't really matter too much. There's an initial distribution, which describes where the agent starts. And there's a horizon, which is like how many time steps the agent is trying to plan for. So just to fix all the ideas, maybe the state is the position of the agent. The action is, go north, south, east, west. The transition operator will move the agent to the right when it says go east. And maybe the reward function is just 1 if you take an action that puts you into the charging station. And the agent is going to interact with this environment in an episodic process, where the episode starts by sampling the initial state S1 from the initial distribution mu. And then the agent will make capital H actions. So in each action, the agent will observe the current state that's given by SH, choose an action that's given by AH, and it's in the action set. Then the environment is going to sample both the reward and the next state. The reward is sampled from this reward function, and the next state is sampled from the transition operator. And so this is going to proceed for capital H steps. And at the end of the episode, the agent has collected some total reward, which is the sum from time step 1 to capital H of all of the rewards. And so the agent is going to try to optimize this. So this is like all of the ingredients and like what one episode looks like. In order to start talking about algorithms, I think we need a few more definitions. This will be the last slide of definitions. So the first concept we need to understand is a policy. And a policy is a mapping from the state space to the distributions over actions. And you can think about this as just some strategy for making decisions. You're in some state. The policy is recommending that you take some action or some distribution over action. You can decide to follow the policy or not. Right. So that's just some strategy. I have some things in parentheses here. Markov means it only depends on the state. This is actually quite fundamental, but I won't talk about it too much. The other one is it may also depend on the time step H. This is because we're in this sort of process where there's a finite time step. So you might want to change your behavior if you have few time steps left. So this would be non-stationary. Now, every policy has some, if you follow a policy, you can expect to pick up some reward. And this is denoted by the value in the MDP. It's the expected reward you would get if you follow this policy. And I'm denoting this by J of pi semicolon M. And what I'm writing on the right-hand side is the sum of the rewards when you play out one episode following using policy pi to pick all the actions. So that's what the expectation of the subscript means. And actually the objective in the MDP is to, sorry, let me close this Zoom window. Okay, I can't. Okay, the objective in the MDP is to find the policy that has the best value. This is the policy that collects the most reward on average. And I'm going to denote that by pi star. Now, okay, so maybe one strategy for finding a good policy is to just compute this number for every policy. The first question is, how would you compute it even for one policy? And for this, it turns out there's a very simple like recursive formula for doing so. And this is given using the concept of a value function. So the value function describes how much reward can we expect to get if we start in state S, first take action A, enter at time step H, and then follow some policy for the rest of the time steps. You can think about this as like the reward to go. So, and I denote this by QH pi, and it's like the sum of the future rewards starting at time step H in state S and taking action A. And this object has a recursive formula where you look at the immediate reward and then the subsequent value function for the policy pi, where the AH plus 1 is chosen using the policy pi. The reason I'm showing you this is because some very similar formula also describes the optimal policy. And this is given by this Bellman equation, which is one of the central objects in reinforcement learning. So this is, it looks like the same thing as what I have in the line above, except that instead of taking the next action AH plus 1, following some policy, I take the action that maximizes the next Q function, the next value function. So this is just some formula. Actually, we won't use it too much in the talk, but I want to show it to you because it's somehow very fundamental to the whole theory. And maybe the main thing to understand here is that actually this function encodes the optimal policy, which I'm not going to prove to you today. And the optimal policy is the one that takes the greedy actions according to this Q function. So it looks at what does this function think about every action and which one does it think has the highest value? And it takes that action. So this is like, we'll only use it in the next slide and we won't use it after that. So these are all the basics. Maybe the first question to think about when you write down this model is, can we even compute the optimal policy efficiently? And even when the MDP is known. So when I know the dynamics, I know the reward, I know the initial distribution, how do you efficiently compute this pi star? And the answer, maybe as alluded to on the previous slide, is you can use dynamic programming. So the way to do this is you create this dynamic programming table where the rows are indexed by states and actions, and the columns are indexed by the time step. And what I'm going to put in every entry is this QH star function for the state and action. So that's what I'm going to put in every entry. And the main idea is that actually to compute one of these entries, you only have to look at a few entries in the next row or in the next column. So you can like fill this table in column by column. And once you have the Q function at the beginning, you know how to write down the optimal policy. So the details are, I'm going to display them on the left. So you start with, at the last time step, you set the Q function to be all 0 because there's no more reward you can get. And then you go backwards in time from capital H down to 1. And you compute the QH star function via the recursive formula, which I showed you on the last slide. And since you've already computed the one for time step H plus 1, this is just something very easy you can do. And then at the end, you output this policy that looks at this QH star function and takes that greedy actions. If this was too fast, that's okay. I think all I really want you to take away is that it's not very hard to compute the optimal policy for any known MDP. So this is a computational question, but I think I'm more interested in this like a statistical question, which is if you don't know an MDP and you just get to interact with it, how do you learn the optimal policy pi star? And in particular, how much data would you require? So this is the statistical question that we're going to talk about for the rest of the talk. So here the picture is, you're this robot, you're trying to find a charging station, but you actually don't know the world. So you don't know where the water is, you don't know where the charging station is. And all you get to do is, you take some actions and you'll advance to whatever position you advance to. And I want you to figure out how you can get to the charging station. And maybe you shouldn't have to interact with the world too much to do so. So that's the idea. And to formalize this, the learning protocol is we're going to complete capital T episodes. And in each episode, we're going to start from, roll out one episode like I showed you earlier. So you're going to start from the starting state. You're going to observe, each time step, you observe the current state. You get to choose what action you want. And then the environment will advance the dynamics and the reward. And at the end of these capital T episodes, you output some guess for the optimal policy. That's called pi hat. And we're going to measure the performance by asking if your policy pi hat has value that's about as good as the value of pi star up to some accuracy parameter epsilon. So this way of measuring performance is called PAC reinforcement learning, or probably approximately correct reinforcement learning. And formally, what we're going to ask is I'm going to give you two parameters. One is epsilon and one is delta. Epsilon describes the suboptimality I'm willing to tolerate, and delta describes some failure probability that I'm willing to tolerate. Maybe with probability 0.001, I allow you to output whatever you want. And what you have to do is you have to ensure that the policy you output pi hat is at most epsilon suboptimal relative to pi star with most of the probability 1 minus delta. And what I want is that the number of episodes you require is polynomial in all the relevant parameters. The number of states, number of actions, time horizon, 1 over the accuracy, and logarithmic in 1 over the failure probability. So this is what we're going to try to achieve.
Akshay, if you don't mind, I'm going to ask a quick question that maybe on behalf of, it might be something that attendees here are wondering. So in your learning protocol, it does not allow for the agent to restart at the beginning of the process again and again, right? And
it does. It does. So every little t, the starting state is S1 from mu.
Okay.
So you roll out capital H steps where the dynamics are evolving as they are, and then you reset to the starting distribution for the next episode.
Great. And things will become more difficult, I guess, if you are not allowed to do the restarting at all.
Yes. So, right. Okay. Maybe your question is, this is like the easiest formulation to explain things. There are many, many other formulations. And actually, the paper I'm explaining does not discuss this formulation at all. But this is actually easier for me, at least, to think about and to convey the main ideas of what they prove.
Great. Makes complete sense. Thank you.
Okay. Good question. Maybe it's a good time to pause. Are there any other questions? Okay. Let me keep going. So this, I'm going to explain to you.
Actually, there is a quick question.
Okay.
Somebody asks, is pi star known?
Pi star is not known. So we're going to try to find something that is as good as pi star without knowing pi star or the MDP at all. So we don't know this T operator, we don't know the R operator, we don't know mu. So we don't know any of those things. We don't know pi star. How do we, solve the task efficiently? That's the idea. Solve the task. I mean, how do we get to the charging station? Or how do we get reward that is competitive with this object that we don't know about? Good question. Okay, so this is what we're going to try to do. And this is sort of very different from supervised learning because we get to choose the actions. And these will actually have a significant impact on what we observe. So this is sort of hinting at the central challenge of exploration. So let's just talk about this a little bit. So maybe a natural thing to try is to just take all the actions randomly. I get to choose what actions to take on every episode. Maybe let's just take them all randomly. And intuitively, maybe we'll sort of see everything that we can see. And so we'll be able to learn about what's going on at every state. Formally, you do have non-zero probability of seeing every state, but this probability can be extremely small. So you won't actually learn efficiently when you do this. And just to drive this point home, let's consider an MDP that looks like this. This is kind of called a combination lock. So the agent will start in G1, that's the good state. There's two actions, and maybe they have different names. And one of them will take you to G2, that's the good state at the next time. The other one will take you to B2, that's the bad state at the next time. From the bad states, you're kind of stuck in this chain of bad states as you advance. From the next good state, there's some other action that takes you to the next good state and so on and so forth. And you only get reward if you're in the good state at the last time and you take the right action. But if you look at most of the trajectories, if you take actions randomly, say, with exponentially small probability, only with exponentially small probability will you actually see any reward. And so this kind of construction can be used to show that uniform random exploration will result in like at least 2 to the h samples required to see any reward, and consequently 2 to the h samples required to learn the optimal policy. So this sort of shows a failure for uniform random exploration, and we will actually have to do something quite a bit smarter. Okay, so that's the example. Let's talk about how we can solve this. Maybe the first thing to think about is just staring at this example. If we do take random actions, we'll spend most of our time in the red chain, in the bad chain, and we'll spend some time at the good states early on in the process, like at G1, G2, G3, just by taking random actions. So what we want to do is kind of bias the exploration to do the things that we haven't done yet. So we don't care about spending time in the bad chain because we've seen a lot of information from there. And we don't really care that much about staying in the early good part because we've already seen a lot of stuff there. What we really want to do is like nudge that agent to go take the actions it hasn't taken before and bias the exploration towards the unknown stuff. So this is the idea of like planning to explore. And the idea is somehow we should keep track of the states and actions that we've seen many times or visited frequently. And then we should maybe here's one way to implement it: build a transition model over the stuff we've seen many times. And so this will be like, if we've seen something many times, then maybe by concentration, we can argue that the dynamics we can estimate there are actually quite accurate. And so we can build a transition model that's like quite accurate over the states that we've seen many times. And so this will look something like this. Maybe when we're collecting, we run around for a little bit and we've seen, from the state all the way on the left, we've seen both the two actions many, many times. So we'll call them known. And so all the blue ones are things we've seen many times and we have good estimates. The red ones are all things we haven't seen many times at all. And we're going to, send them to something that we'll call an absorbing state. I'll tell you more details about this in the next slide. And then what we'll do is we'll just plan to visit the states we haven't seen very much, or plan to visit the absorbing state. And we'll see that we can actually formulate this via dynamic programming, just like the way we were planning in a known MDP. So the idea is, we have this model where there's a bunch of unknown stuff that's represented by the cloud. We're going to plan to visit the unknown stuff. And when we do so, if we deploy that policy in the true world, we might actually discover learn something new. Like we'll learn that this bottom transition is the loop. And then we do this again, and maybe we discover that there's even a new state, and so on and so forth. And so as we go, we'll keep sort of expanding what we know by forcing ourselves to visit the cloud. So that's the idea. And so this is sort of the algorithm, the idea that is behind this algorithm called E-cubed, that's due to Michael Kearns and Singh. And let me try to explain the algorithm on one slide. So there's sort of two parts. The first part is how to construct this absorbing MDP. I'm going to show you on the left, and I'm going to show you the algorithm on the right. So actually on the left, I'm going to show you a construction of two MDPs, and they're going to have the same transition operator T, but they're going to have different reward functions. And so we'll go through this a bit slowly. Okay, so the idea is to construct an MDP that looks like this. So the blue transitions are going to be the ones that you know, and the red transitions are going to be the ones that you don't know. And they're going to transit to some fake state that I'm going to create called the absorbing state. And so what I'm going to do is I'm going to look at each state action pair. I'm going to check if you have enough samples from that state action. So maybe poly number of states over epsilon square samples. And if so, that means I sort of have good estimates. So these will be called the known states. And I have good estimates, which means that maybe just looking at the empirical transitions that I've seen so far is a good estimate of the transition operator. And just looking at the empirical mean reward is a good estimate of the true mean reward. And so this will be the exploitation reward, which I'm denoting by r hat exploit. Remember, there's going to be two reward functions. So this is what I do for all the blue arrows in the figure. I know what's going to happen, or I can approximate it very well because I've seen enough data. For the red arrows, if I don't have enough data, I'm going to just send all of these state action pairs to the absorbing state. So my estimate for the transition operator, which is going to be totally wrong, is going to just say go to the absorbing state. And I'm going to set up this exploration reward to give you a reward of 1 if you are at this state and you're taking this action. And then I'm going to just make the absorbing state loop on itself. And I'm going to set the reward for both the exploration and the exploitation reward for the absorbing state to be 0. So there's two reward functions. There's the exploration reward and the exploitation reward. The exploration reward is going to encourage the agent to take some red arrow. The exploitation reward is going to, you're not going to want to take the red arrows. You're going to stay in the blue area and accumulate like the real reward that you can in the blue area. So these are sort of the two MDPs, right? There's, they have the same transitions, but one has exploration reward and one has the exploitation reward. And what the algorithm is going to do is it's going to try to maximize the exploration reward in this MDP and see how much value it can get. And if this value is high, it's going to just deploy the optimal policy for maximizing the exploration reward. And what that's going to do is it's going to push towards the red arrows and visit the red arrows a lot. So that is going to expand what the known set is. On the other hand, if the exploration reward value is not very high, then somehow no policy can get to the red arrows because the optimal policy cannot do it either. And so no policy can get to the red arrows. That means that if we just maximize the exploitation reward, we should be in good shape. So that's the idea and that's the intuition. So let me just write down some pseudocode. So we're going to repeat. First, we're going to build these two absorbing MDPs. I'm going to denote them by m hat k. I'll always explain what the reward function is. Then we're going to compute the optimal policy for maximizing the exploration reward in the absorbing MDP. We're going to check if that policy actually does visit the absorbing state. So we can just check what's the probability that this policy visits the absorbing state in our estimated absorbing MDP. And if that probability is big enough, we know that this policy is going to visit some red arrows, and so we can collect some trajectories to make progress. Otherwise, we'll compute the exploitation policy to maximize the exploitation reward in the absorbing MDP, and we'll just stop and output that. That's the answer. That's what we're going to output as our estimate. Okay, so that's the algorithm. And Vidya, how much time do I have?
I'd say about 3 to 4 more minutes, because I also want to leave a couple of minutes for questions that people are having in the chat.
Okay, maybe let me tell you the first part of the analysis. So the first question to understand in the analysis is like, what happens if we have no unknown states? So over here, what if no states actions fit into this else clause? Are we actually done? So this is what's given by the simulation lemma. This is probably one of the fundamental lemmas in the design of RL algorithms. And so this is just somehow it's like a perturbation result on what happens if you have two MDPs whose dynamics and rewards are very close to each other. Are the value functions close to each other? So let's just consider two MDPs, M1 and M2. They have the same state and action space. They have different transition operators and different rewards. But the transition operators and the rewards are very close to each other. So the transitions are close, let's say in total variation distance. The rewards are close in their means. Then it turns out that for any policy, the value of the policy in one MDP is about the same as its value in the other MDP. So this is what I mean by simulation. If you built an MDP model for the true world that satisfied these two approximation guarantees about the dynamics and the rewards, then the value of policies is also preserved, or the perturbation is not too much. And just some immediate consequences are that the optimal policy in M1 is the near optimal policy in M2. And so that means just if that's true, then if we can learn all the transitions and the rewards, we're done. And note that by concentration, we'll set up the sample complexity so that any known pair actually satisfies the preconditions here. That's what it will mean to be known. Okay, so to analyze this algorithm, you have to do something like a fancier simulation that involves 3 MDPs. So one is the true one is the estimated absorbing MDP, and one is the true absorbing MDP. And I guess I probably don't have time to do this. But once you set up these 3 things, you'll come up with some fancier simulation lemma like the one I'm showing here. And you'll be able to show, okay, let's just move on. This is too much. So that's like, there's some argument to establish correctness. And then there's like a potential function argument to establish the termination. And this is something like, if your exploration policy actually visits the absorbing state, this can only happen so many times, because every time it visits the absorbing state, you'll slowly be making things that were previously unknown known. And there's only a few things that are, there's only essay things that are unknown in the beginning. So that's how you do the termination. Let me just tell you like some high level version of the theorem. So this is due to Kearns and Singh. So this algorithm, you can set it up so that it outputs an epsilon suboptimal policy with probability at least 1 minus delta using poly SAH 1 over epsilon log 1 over delta trajectories. And this is actually the first algorithm to do so. And you can see this result is like 20 years old. But I think even then it was viewed as a breakthrough. And now this is sort of like the foundation for a bunch of more modern work. And just in terms of modern work, just in focusing on tabular MDPs, there's been more recent work on what is the optimal sample complexity. And this scales much better than what I'm not showing you, but the bound of Kearns and Singh. There's also questions about instance dependent kind of results, or like maybe what does it mean for an MDP to be easier than the worst case? And how do we quantify that and get algorithms that can adapt to easier instances? And there's also some other formulation where the rewards are normalized in a different way, where you can actually get guarantees that are independent of the horizon altogether. So this is like one topic that's quite active in the modern RL theory world. But actually all of those things are still only focusing on both exploration and credit assignment. So another direction that people are starting to work on now over maybe the last 5 or 7 years is about how to do exploration, generalization, and credit assignment at the same time. And so this question is going beyond tabular MDPs and is asking, how can we use function approximation to generalize across states so we don't have to pay even poly S, say? And so here there's like a bunch of work on linear function approximation. And then some work that me and people at MSR have been doing is building a theory for nonlinear function approximation and some algorithmic toolkits for methods that are, I guess, in principle, compatible with like deep learning. Beyond this, addressing all 3 of these challenges, there's many, many other questions, like what do you do in sequential multiplayer games? How do you deal with situations where the state is not observed? How do you do reinforcement learning when you just are given a batch of data and you're not allowed to explore at all? And many, many other things. So the bottom line, I would say, is there's many interesting topics to explore. There's many references I could have pointed to. This one has the shortest URL. So maybe this is a good place to start reading if you want to read more, and they will have many references there as well. With that, I'll stop, and maybe there's some time for questions.
Thank you very much, Akshay, for a great presentation. Gives a good sense of exploration and reinforcement learning. Awesome. So I think I do want to get a couple of the questions that students have asked answered. So question 1, in this whole paradigm, can you do better if you can choose where to start in every episode?
I think certainly other algorithms will also work. Okay. If that's an answer to that question. Yeah, I am not sure about improvements in sample complexity compared to the optimal. Mm-hmm. That seems not so likely, but I think other algorithms will definitely work.
Yeah, like a broader class of algorithms than the
Yeah. So actually these like policy gradient methods rely on the starting distribution covering the states. If you've heard about policy gradient, those will work when you can choose where to start.
Awesome. Question 2. So the transition kernel is time dependent. Does this formulation include the case where transitions or rewards can be chosen adversarially? Or is everything still a stochastic process?
Yeah, so here everything is stochastic. There is some work on some versions of adversarial things. I think the most common one is the transitions are still stochastic, but the reward function is adversarially chosen in each episode. And here you have to, like this algorithm will not work, and you have to use some techniques from like adversarial online learning. That's actually very active, I think, today also.
Yep. And I'm going to ask this last question because it's good for a learning theory audience. Is there an analog for the notion of VC dimension or the sample complexity of the hypothesis class for this type of result in RL?
Yes, it's in this paper on the second line, I guess. So I don't know, there's something. So like it's beyond what the complexity of the function class is. It's some, I think the current, it's certainly not as crisp as VC dimension, but there's some conjectures or some ideas that kind of work. And these are all about some interactions between the function class you're using and the MDP dynamics as well. So one idea is in this paper that I'm referring to.
Perfect. Thank you so much again, Akshay.